Before a large language model is ready for the real world, it goes through three major transformations. First, pre-training gives the model broad word knowledge and linguistic abilities. Next, supervised fine-tuning teaches it how to format responses, hold a conversation, and act like an assistant. But the most critical step is alignment, shifting from how to behave to what to value: judgment, safety, and reasoning quality. In this video, I'm breaking down three dominant alignment engine shaping modern LLMs: PPO, DPO, and GRPO. Now let's look under the hood at what happens during a single training step of PPO. Once our active model generates a response, we take that completed query plus response pair and feed it simultaneously into four models in the memory. First, we run it through our active model, the trainable actor, and our frozen reference model. By comparing their token log probabilities, we calculate the KL divergence, which tells us how far our active policy or model is drifting from its baseline. Why do we need this? Because we have a dual objective here. We want to align the model to human preferences, but we cannot afford to destroy its core language fluency, general capabilities, or pre-trained word knowledge in the process. Second, the frozen reward model evaluates the full query plus response and outputs a raw reward score. We then combine these two signals. We take that raw reward and subtract the KL penalty. This gives us our composite reward. This encourages high-quality responses while penalizing unnatural drift or reward hacking. But here's the actual challenge. The reward is a single score arriving only at the very end when the sequence is complete. Yet the policy made a decision at every token level. Which token deserves the credit or the blame? And how good or bad that score is. This is where our value model comes in as the critic. It estimates the expected score from each step forward, giving us a reference baseline at the token level. By subtracting the value baseline from the composite reward, we get our advantage. Advantage answers a key question. Did this specific token perform better or worse than what we expected? Finally, PPO takes the advantage signal and pushes it back into our active model through this clipped objective. Let's unpack it. We have a new term here, and that is rho of t. Rho of t measures probability ratio that asks this question. Compared to the previous policy that actually generated this text, how much more or less likely is our updated model to choose this token? We multiply that by the advantage. Positive advantage pushes the token probability up because we want the model to generate more tokens like this. And negative advantage pushes it down. The clip and the min here are safety brick. They cap how far a single update can move. So one overconfident token can destabilize the whole policy. We average over every token, an example, and maximize it. In short, advantage set the direction, ratio measures the change, and the clip keeps us from going too far. And as we update the policy, we also update the value model to keep the baseline prediction calibrated. PPO is powerful, but you probably can already feel the operational headache. Running four massive models in memory simultaneously is complex, brittle, and extremely expensive. What if we could skip the reward model and the RL training loop entirely and optimize directly on human preferences? That is the core insight behind direct preference optimization, or DPO. Let's see how DPO works. In step 1, we have the input pairs. We start at the top with a static data sets of the prompts paired with two completion, a chosen response and a rejected response. There's a dual forward pass now. We feed these prompt response pairs through only two models, our trainable active model and our frozen reference model. Both models compute token log probabilities for both the chosen and rejected responses. Then we have the implicit reward. When we subtract the reference log probs from the active model's log probs, we get the log ratio. This is the beauty of DPO, and that is the log ratio acts directly as an implicit reward, measuring how much more our active model prefers a response compared to the original baseline. Next is our DPO loss and optimization. We plug the implicit reward difference between winning and losing response into our DPO loss, and also notice the negative sign in front of the loss. Our conceptual goal is to maximize the probability of preferring the chosen answer. It's always that. But the standard optimizers minimize loss using gradient descent. And that's not something new here. If you look at the literature of deep learning, we always prefer to minimize negative of the objective function that we wanted to maximize. And that is the same thing, but it's just easier to do using gradient descent. Adding a negative sign converts our objective into a standard negative log likelihood of loss. And then backpropagating this loss pushes the policy gradients directly into our active model, increasing the likelihood of preferred completion, suppressing rejected ones, and preventing drift. While DPO gives us simplicity by training offline, it loses the ability to dynamically explore new solutions during generation. But going back to the full online PPO means paying the heavy memory penalty of the reward critic architecture. This brings us to the Group Relative Policy Optimization, or GRPO, which is the engine powering modern reasoning models like DeepSeek-R1. The key breakthrough here is keeping the exploratory power of online RL while completely throwing away the memory-heavy critic network. So we're going to get rid of the critic model completely here. So let's see how this works. In step number 1, we have group rollout. We start with a single query at the top. Our trainable active model generates a group of n diverse candidate completion, O1 to ON. Dual parallel evaluation. On the left, our rule reward engine evaluates all n completion. For math, logic, or code, this is often a fast deterministic checker, like unit tests that return raw scalar scores. Simultaneously, on the right, all n completion pass through the frozen reference model to compute baseline token log probabilities. Then we have the statistical group advantage. Instead of training an expensive critic or value model to predict baseline values, GRPO calculates the baseline directly from the group. The advantage for each completion is the statistical z-score. It's a score minus the group mean divided by group standard deviation. Completions that beat the group average get positive advantage. Those below get penalized. In the next step, we have KL divergence, as always. By comparing the token log probs of the active model and the reference model, we make sure the model stays grounded. Unlike PPO, this is not folded into per token reward. It stays as the explicit penalty term in the overall objective. And then in step number 5, we have GRPO objective function. Let us look at how this equation is a structure. The outer summation averages over all n completion in our group, while the inner summation averages across every individual token in that completion. Notice the 1 over length normalization factor. That is so important. It prevents the model from gaming the loss by simply generating overly verbose text to accumulate reward. Also notice that our advantage, A hat I, is calculated once for the whole sequence. It evaluates the complete reasoning pass, while the probability ratio rho IT operates at each individual token. The clip function, as always, restrict that token probability ratio within a safe bound, typically 0.8 to 1.2. And the min operator takes the conservative bound, so a single lucky batch can destabilize our policy updates. Finally, we subtract the KL penalty against the reference model to prevent policy drift. Backpropagating this loss pushes policy gradients straight into our active model. All right, now it's time to do a head-to-head comparison. Let's put this side by side. This table gives you the full practitioner decision framework in a single view. So we have PPO, DPO, GRPO head-to-head, and we are going to start with looking at paradigm and exploration. This is the primary dividing line here. PPO and GRPO are online RL methods. They generate fresh rollouts during the training and learn from what the active policy creates. That enables dynamic exploration. DPO is offline supervised learning on static data. It does not generate new text during training. It simply reweights the fixed preferences it was given. Let's take a look at baseline mechanism. Every method needs a baseline to evaluate relative quality. PPO trains an entire second neural network, the value model or the critic. DPO uses the frozen reference model as the implicit anchor. GRPO uses a simple statistical trick. It computes the baseline straight from the group mean of multiple completions, ditching the critic network or model entirely. And then we have the reward source. PPO relies on a separately trained neural network. DPO has no reward model at all. The reward is implicit in the policy log ratios. GRPO primarily leverages deterministic, verifiable rules like test suits and format checkers, though it can also incorporate a reward model optionally. If we look at the GPO memory, this is the operational bottleneck that we have. Like PPO is very high because you must hold 4 models in VRAM at once: active, reference, reward, and value. DPO is very low. It requires only the active model and the reference model. GRPO sits in the middle, moderate, because dropping the critic removes significant memory overhead compared to PPO. Now, that brings us to best use case. PPO excels in subjective, open-ended chat, where quality is nuanced. DPO is the fast, efficient pass for conversational alignment where static preference pairs are available. GRPO is the weapon of choice for verifiable reasoning, mass code, and structured problem solving. In short, DPO trades online exploration for speed and simplicity. PPO offers complete optimization flexibility at the highest compute cost, and GRPO provides the sweet spot for reasoning tasks, keeping online exploration alive while stripping out the expensive critic.